If you look at the digital architecture of any office, school, or home, you will find a local area network, or LAN. This is a closed loop of cabling and wireless signals that connects computers, printers, and phones within a single physical space. The central anchor keeping all those local devices talking to one another is a piece of hardware called a switch. This schematic shows how that local communication works. The switch passes data between devices using MAC addresses, the permanent physical identifiers burned directly into the hardware by the manufacturer. Inside a building, switches deliver files from one desk to another with high efficiency. However, because they rely strictly on these physical hardware addresses, switches cannot see or communicate with anything outside their own immediate environment. Consider a scenario where a computer on your network, let's say it uses an IP address starting with 10, needs to pull a web page from a server on a completely different network that uses an IP structure starting with 192.168. Your local switch fails to process this request. It only understands physical MAC addresses, which means it lacks the programming to interpret distinct external IP network structures. Crossing this boundary requires a device operating on a higher tier of networking logic, known as Layer 3 of the OSI model. Since physical hardware addresses cannot scale to cover billions of devices globally, isolated networks require a dedicated logical navigator to translate data and bridge the gap. That navigator is the router. A router is a highly specialized computer. Inside the chassis, you will find its own distinct CPU, RAM, and a dedicated operating system designed entirely for moving network traffic. This flowchart compares the router with the modem. Modems take the raw analog signal from your internet service provider and convert it to a digital binary format. The router then takes that digital connection and splits it into multiple logical pathways for your devices. To manage this, a router uses two distinct physical interfaces. One interface is plugged internally to the LAN, and the other is connected externally to the Wide Area Network, or WAN. By straddling this physical boundary, the router acts as the default gateway, the inescapable exit point for any local device trying to access the internet. When you send data, it arrives at the router broken into smaller segments called packets. The router's first action is to read the destination IP address located inside the packet's header. The router compares the destination to its routing table, an internal database of every possible network path. It scans for the specific matching network. If multiple paths exist, it checks the metric value, always choosing the path with the lowest metric, the fastest, lowest cost route. These tables aren't static. Routers use dynamic algorithms to constantly update their paths as global network conditions change. Once the optimal path is identified, the router physically forwards the packet to the next hop towards its destination. This calculation happens in milliseconds, ensuring that global data moves efficiently without entering infinite loops or causing data collisions. The device in your home or office is an edge router. It sits at the perimeter, acting as a border guard that handles security firewalls and translates your internal IP addresses for the outside world. In contrast, core routers are the massive backbone devices used by ISPs. They are stripped of security firewalls to focus entirely on maximum packet switching velocity across vast distances. As seen in this diagram, edge routers pass their data up to these core routers, which then navigate the distances between cities and continents. The internet is not a nebulous cloud. It is a physical hierarchy where specialized edge and core routers pass data up and down the chain. Because edge routers are the absolute gatekeepers of the local network, basic security, like changing default administrator credentials, is a mandatory step in protecting the LAN. Administrators also use the router to set quality of service rules, which prioritize bandwidth-heavy traffic, like video calls, over background tasks. Without the router's Layer 3 intelligence, global connectivity collapses. Individual networks would be unable to communicate, effectively ending the internet as we know it. The router maintains a constant, silent workload, reading headers, comparing metrics, and updating routing tables every second of every day. The router provides the logical bridge that prevents the internet from shattering into isolated hardware islands, making seamless international communication possible in milliseconds.